Hello everyone. We will now be solving questions regarding gravitation, and I've compiled around 5 to 6 questions for you, and this will represent a very good sample size regarding gravitation, and it covers most of the topics. So I hope you'll get a good understanding from these questions. Let's start with the first one. This is from May, June 2023. Question 1 says that state Newton's law of gravitation. Now, usually, whenever they ask you about definitions or they ask you about laws or principles, one of the best ways to answer it is using the formula. So we know that the formula for gravitation is F equals to G over R square. But Newton's law specifically said that force is proportional to the product of the two masses, which is the big M and the small m, and it's inversely proportional to the square of the separation. So force is directly proportional to the product of the two masses, and it's inversely proportional to the square of the separation. So in reality, you can just write that as your answer. So simply, because it's 2 marks here, the first mark will be that the force is directly proportional to the product of the two masses, and another mark will be that it's inversely proportional to the square of the separation. Right? That's it. Okay, question 2 says that a satellite is in a circular orbit around a planet. Whenever you hear about this term circular orbit, you should recall back to circular motion and try to link this topic with that one, right? They say that the radius of the orbit is r and the period of the orbit is t. The planet is a uniform sphere. And the reason why they say uniform sphere, if you remember, is that because we can apply this formula to it, right? Because this only works for uniform bodies. That's why they are called point masses, right? Because we assume the whole object is uniform. Use Newton's law of gravitation to show that r and t are related by this equation, whereby m is the mass and g is the gravitational constant. So let's try to visualize this, okay? I really like to visualize questions whenever we are proving something. So we have a planet over here, and you have a satellite which is going in a circular orbit. So maybe you have this satellite which is going through a circular orbit towards this planet. Now the radius of this orbit is r, and the period of the orbit is t. The planet is a uniform sphere. So obviously this is the planet, right? And it has a center over here. So now we can see that this satellite will actually be pushed towards the center, and this is the centripetal force, right? And this force is provided by what? This force is provided by the gravitational force, because we know that the gravitational force is providing the centripetal force. It's what is making it to go towards the center. So you can start by writing that Fg provides Fc, right? And then you can just equate these two equations. So Ft equals to Fc, and we know what's the equation for Fg, which is Gmm over r square equals to Fc. Now centripetal force, we learned two formulas for it. There was mv square over r, and there was also mr omega square. Now between these two, which one do you think is more reasonable to use in this question over here? So to answer that, you have to look at your data, right? In your data, you have the period time t. Okay. Now between these two formulas, which one involves the period time t? The one with the omega, if you expand it, in fact you get mr 2 pi over t square. So you can see that the one which is more appropriate to use in this situation will be this second one. So you just replace this with this. So mr 2 pi over t square. Now we can simplify this equation. So I just crossed out the small m and the small m over here. Then we also have r square here, and we have r over here. So we can cross multiply this to form r cubed. And we can also expand this bracket as well. So we get gm equals to, so r squared times r will be r cubed, and then expanding the whole thing here will be 4 pi square divided by t square. Yeah, because the square applies to both the up and the down parts. Then when you cross multiply these two, you get gmt square equals to 4 pi square r cubed, which you can see is this one, right? So we have shown the relationship between these two. Let's continue with question C. This one says that the Earth may be considered to be a uniform sphere of this mass and this radius. A geostationary satellite is in orbit around the Earth. Now, before we continue, I want you to recap what are the features of a geostationary satellite. The first thing that we know about it is that it has a period of 24 hours. And another thing that we also know about the geostationary satellite is that it's equatorial, right? So it travels in an equatorial plane. And last thing is that it always stays at the same distance above the Earth. So now they say that use the expression in B to determine the height of the satellite above the Earth's surface, right? So you have to determine the height of the satellite above the Earth's surface. This question is a bit tricky, so you have to be very careful here. They're saying determine the height above the Earth's surface. Okay, so remember this drawing that we drew over here. Now, if this is the radius r of the Earth, the satellite is at a certain height above this Earth's surface, yet? Because this is the Earth's surface and the satellite is above the Earth's surface at a certain height. So what we have to find is we have to find this height h. Okay, that's our goal. And how will we do that is using this formula over here. So let's try to plug in the values and see what we get. So for the g, we have 6.67 times 10 power negative 11. We have the mass as 5.98 times 10 power 24. Now for the period time t, what will be our value of t? Now if you read the question, they say this is a geostationary satellite and it has a period of 24 hours. So in fact, you are going to use this one as our period time t, because the period time is defined as a time taken for it to complete one whole rotation, which will be 24 hours. So because the formula uses time in seconds, we have to convert this into seconds. So we will do 24 hours times 60 minutes times 60 seconds. And this will be equal to 4 times pi square times r cubed. We don't know what is r, right? Because this r will be the total distance from here until here. So I don't want you to get confused between that r and this r. Let's call this small r. And this will be the radius of the planet. But the r in this formula is the distance between the satellite and the planet. So between here until here. And this r is specifically just the planet itself, okay? And here they've given you the radius of the planet of the Earth. So doing this calculation gives you r to be equal to 4.22 times 10 power 7 meters. But again, we want to find the height. So what we will do is that height will be equal to the capital R minus the small r. So this answer, 4.22 times 10 power 7, we will subtract it with the radius of the Earth, which was 6.37 times 10 power 6. And we will get the final answer as 3.6 times 10 power 7. Okay, going on to the next question. They say that another satellite is in a circular orbit around the Earth with the same orbital radius and period as in satellite in C. Calculate the angular speed of the satellite in this orbit, and you have to give a unit with your answer. Okay, so we are going back to circular motion again with this. If you want to find the angular speed, what is the formula for angular speed? We know that angular speed is represented by omega, and we know that omega is equal to 2 pi over t, right? And because they are saying that it's the same orbital radius and the same period, we can directly plug this into this formula. So we get 2 pi divided by the period time, which will be 24 hours times 60 minutes times 60 seconds. And you shall get your answer as 7.3 times 10 power negative. And the units for this, you can directly get the units from the formula. So this top part over here is the degrees or the rotation, right? And the rotation is represented in radians. And this bottom part is time, so this will be seconds. So our unit will be rad seconds negative 1. Okay, going to the last question. They say that despite having the same orbital period, so which is 24 hours, the orbit of the satellite is not geostationary. So there's two ways in which this orbit could be different from the orbit of that one. Again, this comes back to the features of a geostationary orbit. And I think I forgot one more over here. In the features, we have one more feature, which is a geostationary orbit travels from west to east, right? That's one of the main features of a geostationary orbit. So if this one is not geostationary, that means that it could be traveling from east to west instead of west to east. And for another one, you can just write the opposite of this. So a geostationary orbit is in an equatorial plane. So this one will not be in an equatorial plane, right? So not in an equatorial plane. I have also attached the marking schemes for you, so you can refer to that as well if you need additional help. Let's go to the next question. State Newton's law of gravitation. So we have just done this in the first question already, so I'll just skip over this, right? Just write solved. A distant star is orbited by several planets. Each planet has a circular orbit with a different radius, but each planet orbits at a constant speed. Explain whether the planets are in equilibrium. Okay, now going back to your AS level, what are the conditions required for something to be in equilibrium? So first condition is that there shall be no resultant force, and another condition should be there is no resultant moment. Okay, we are not talking about moments over here, so I'll ignore this one, but let's talk about this one. There shall be no resultant force. Now we know that what's the formula for resultant force? Resultant force is mass times acceleration. Okay, so if the acceleration is constant, then the resultant force is constant, right? So if something is in equilibrium, it means that its acceleration has to be constant. Okay. Now, if they say it has constant speed, does it mean it has constant velocity as well? That's not necessary because velocity is a vector. And if you have a star orbiting planets, let's again visualize this. You have a planet here and you have a star maybe just orbiting around the planet. You see that it's changing direction. If it changes direction, then there's a change in velocity. And if there's a change in velocity, there is an acceleration taking place. So in fact, this one is not in equilibrium. So not in equilibrium. Excuse my handwriting. And why is that? Is because change in velocity due to change in direction. Going to the next question. The radius of the orbit of a planet is r and the orbital period is t. Data for some of the planets are given in this figure. So we have this data over here. Each planet has a radius and the period time squared. The relationship between r and t is given by this expression. Show that the constant k is given by the expression k equals to gm over 4 pi square, where g is the gravitational constant and m is the mass of the star. Okay, this looks complicated, but just try to understand the question over here. We know that one thing is happening is that each planet is moving in a circular orbit. Again, whenever you see circular orbit, there should be like a light bulb, like lighting in your brain. Like this is a circular motion question as well. So you have to have this relationship again, Fg equals to Fc. And it's similar to what we did in question 1, right? Now we have to form this expression. And you have to show that the k represents this one. The best way to do this is to equate them and to prove this. Okay, so you will just see how this one forms itself. Okay, so Fg is what? Gmm over r square, and Fc, again you have choice here. Either you do mv square over r or mr omega square, and the answer to that will be depending on the question. Look at the units given here. There is pi, right? And the one where you can get pi from is omega, because omega is 2 pi over t. So it's more easier to use omega in this question over here. So we'll be using mr omega square. Again, we simplify this. So this m and this m cancels out. The r square comes over here, so it becomes cubed. And we also expand the omega. So this becomes gm equals to r cubed, and omega, we say it is 2 pi divided by t square. And we get gm equals to 4 pi square r cubed divided by t square. Again, we cross multiply them, and I'll be going a bit fast here because we have done this in the earlier question. So we get this relationship over here. Now you can see that we have r square over here, r cubed over here, sorry, and we have t square. But over here, r cubed is in the left hand side and t square is in the right hand side. So let's just rewrite this. 4 pi square r cubed equals to gmt square. We want to find the relationship between r cubed and t square, and here there should be k over here. So what we can do is we can divide this by 4 pi squared and divide this by 4 pi squared. So we just remain with r cubed in the middle. Now when you do this, you see that r cubed equals to gm divided by 4 pi square and then t square. This is how we form this relationship. And this one, the whole thing, because it's a constant, can be represented as k, right? So that's how we form this expression over here. Right, now going to the last question. Use data from figure 1.1 for the 3 planets and the expression for k to calculate the mass m of the star. So in this question, what you have to do is that you have to use this relationship, r cubed equals to kt square. Now you see that we have data for 3 planets and we have everyone's radius and the t square. Note that this is t square itself, like this t square will directly be this value. Okay, but for the r, you'll have to cube it. So for example, you take this planet C, you have to do r cubed, and then you, for the t square, you just plug in this value directly. Okay, so you can use any of these 3 planets in the value for k to find the value for k, because k is a constant and it will be the same for each of these 3 planets, right? So you can use any of these to substitute and get the value for k. When you find the value for k, this is the value for k that I found when I substituted it. When you get the value for k, you can use our expression for k, that k was equal to gm over 4 pi square, to get the mass, because they say to calculate the mass m of the star, right? So we have our k, you have your gravitational constant, which is 6.67 times 10 power negative 11. Mass is what you are finding, and we know what's pi. So when you plug this in and you calculate the value for m, you should get 2.1 times 10 power 33 kg. And that's it for question 2. Right, let's go to question 3. And this one is from May-June 2025. The first question asks that define gravitational fields. Again, whenever you get definitions, try to find the formula for what a gravitational field is, right? So when they talk about gravitational fields, this is your gravitational field strength, which is just normal gravity. We know that gravity is just weight equals to mg, right? And this is the gravitational field strength. And gravitational field is the same as gravitational field strength. So what will be the formula for G? G will be the weight divided by the mass. So you can just write it's the force per unit mass or the weight per unit mass, right? And this is how you will define this. So it's just the force per unit mass. B states that the gravitational field strength G at a distance x from the center of a spherical planet of mass m is given by this expression. And this is our normal gm over r squared. Instead of r, they've kept x over here, okay? Where g is the gravitational constant and distance x is greater than the radius of the planet. So what's happening over here is that, let's say you have this planet here, and this is the center. Again, from here to here is the radius of the planet, which is r. But there's a certain mass at the surface here. So they have given you x as the distance between the center of this mass and the center of this planet, right? So between these 2 point masses, this is x. Describe the pattern of the field lines outside the planet that represent the gravitational fields due to the planet. So the gravitational field lines outside the planet is this whole area over here. So outside over here, the whole part. In this space, we know that the gravitational field is towards the center of the planet. So it's acting towards the center, right? So this is how the gravitational field lines are acting. And there's a word for this, and this is called, they are radial. Okay, so radial just means that they are acting in a circular form and they are going directly towards the center. So radial and towards the center of the planet. Okay, so you can just write that. Then they say that explain why for small changes in vertical height near the surface of the planet, g may be assumed to be constant. So they are saying that why can you assume that the gravitational field strength over here, right at the surface, is very close or the same as the gravitational field strength at slightly above the top of it. So let me explain this with a better example. This is the earth, right? This is the surface, and this is you over here. Let's say you jump a bit, you jump and then you try to come down. why is it that the gravitational field strength at the surface is considered to be the same as at a small height above the surface, right? So we have a distance r here, which is from the center of the earth until the surface of the earth, and we have a distance x here, which is from the center of the earth, but together with the r, there's a small distance height over here, which is this h. So we can say that because this radius is too big, then this slight difference in height won't make a big effect in this formula. It's like saying that if this x is maybe 10,000, let's say the radius is 10,000 of the earth, and then you jumped maybe just 1 meter or 2 meters, then just adding 1 or 2 over here will not make a effect to this value of g, right? So what you can say over here is that the radius plus height is approximately the same as the radius itself, because the height is very tiny compared to the radius of the earth, compared to radius of earth. Yeah, I hope that made sense. Now they are saying that assume that the earth is a uniform sphere. For the earth, the product gm is equal to 3.99 times 10 power 14. Determine a value to 3 significant figures for the radius r of the earth. So what you can just do is use the formula for gravitational field strength, which is gm over r squared. You are finding the radius, and you are given that the product gm is that value, and gravity of earth is 9.81, so you can just substitute the values. 9.81 equals to 3.99 times 10 power 14 divided by r squared, and you should get the value of r as 6.38 times 10 power 6. The next question states that calculate the gravitational potential at the Earth's surface and give a unit with your answer. So gravitational potential, we can write this as phi. The formula for this is negative gm over r. So again, we have the product gm, which we got from the previous question, and that was equal to 3.99 times 10 power 14. So we can use that, and we can say that it's going to be negative 3.99 times 10 power 14, and we just got the r over here, which is 6.38 times 10 power 6, and you should get your answer as negative 6.25 times 10 power 7. Also, don't forget that this negative exists because the force is attractive, right? And what will be the unit for gravitational potential? So if you remember from the lecture that gravitational potential is actually the gravitational potential energy per unit mass. So GPE is joules and mass is kilograms. So this will be joules per kg. Now they ask, explain why the GPE of 2-point masses is always negative. Yeah, so this comes back to the same concept again. We say that the force is attractive, right? And you have to give work, or you have to do work to separate the 2-point masses. So by default, the force is attractive, and also we assume that at infinity GPE is 0. So when you have 2-point masses like this, and they are separated by a certain distance, when they are separated until infinity, this is when the GPE will be equal to 0. But all this behind over here is like a number line. This whole is negative. Okay, and that's the end of question number 3.